Log on, tune in, find out. Another good idea from Cambridge.
Okay, I'd like to introduce Robin Evans, who will be talking on variation-independent parameterizations.
Thank you. Okay, so I'll just start with some acknowledgements to the organisers. My PhD supervisor Thomas Richardson and our collaborator James Robbins. Okay, so variation independence, chose the shortest title and therefore the vaguest. What is variation independence? You start with some kind of model, which in my case I'm going to be thinking of as a subset of the probability simplex, so everything's discrete, and it's p-dimensional, indexed by some parameter space theta. And then this parameterization is variation independent if it's just a Cartesian product of univariate things. So another way of thinking about it is I've got a vector of parameters, and if I choose some values for some of those parameters, that doesn't restrict the range of the remaining entries that I could choose. Okay, well, why is this nice? Well, first of all, it gives a sort of form of irrelevance between the parameters, which is formalized in the sense that variation independence is what's called a separaroid. To give a more concrete example, suppose you're going to do some sports betting. You've got Euro 2012 coming up, and you go to your expert sports betting advisor in the pub and say, okay, what do you think the chance of Wayne Rooney being the top scorer is? And he says, oh well, there's a lot of good players, but Wayne's on good form. I'll give him 10% chance of being the top scorer. Say, okay, and what do you think the chance of England winning is? And being a fairly optimistic chap, he says, oh well, okay, I think there's about a 20% chance of that happening. You think, great, okay, but I want to do some more complicated betting. So what do you think the chance of Wayne Rooney being the top scorer is and England winning? And he thinks, well, those two things seem to go together, so I'll give that a 15% chance of happening. And your head sinks in your hands because he said that the chance of Wayne Rooney being top scorer just on its own was only 10%. So you decide to give up on this project, but just as you get home, you think, oh, if only I'd asked him what the log odds ratio between Wayne Rooney being the top scorer and England winning was, because then he could have said any number he liked between minus infinity and infinity, and I would still have at least had a probability distribution to work with. And it might also mean that if you had a search algorithm, say, doing maximum likelihood estimation, you wouldn't have to be very careful to make sure that your algorithm didn't wander outside a valid parameter space. And I think there's also a sort of aesthetic niceness to variation independence. So let's look at a specific class of models. Bidirected graphs like this one, where you have random variables represented by nodes, and you have some bidirected edges between them or not. They're used to encode independences, and they do so by saying that, okay, if you've got two groups of the variables, if there's no edges directly between them, that means those variables are marginally independent. So in this example, 1 is not joined to the set 3 and 4 directly, so x1 is marginally independent of x3 and x4. So if we consider those in the discrete case, specifically the binary case, we've got 4 binary random variables, there's a parameterization of this model which says for each set which is connected, not completely connected, but so in the sense that 2, 3, 4 here is connected, you can get from any node to any other node without leaving the set. Every complete set, you need to know the probability that everything is equal to 0. So in this case, you get these 10 parameters. And they're clearly variation dependent because, as we just discussed, if you have 2 events happening, the probability of them both occurring has to be less than or equal to each of the individual events occurring. So we might ask, can we have this model and can we find a parameterization which is variation independent? So if we start with a sort of very simple example, this is a complete graph and therefore there's no constraints. So it would be very easy to come up with a variation independent parameterization just by saying what's the probability that this happens, and then what's the probability that this happens conditional upon this, and this conditional upon the other two. But we're going to imagine that we're starting with this sort of parameterization where we only can, where our parameters are what's the probability that some subset of the variables is 0. And it turns out that those parameters are valid, it's very easy to show, if and only if these inequalities hold, so on your 7 parameters. And they all involve the probability that everything is equal to 0. So you say, okay, how can I take this parameter and turn it into some variation-independent version of itself to make sure that all these bounds are satisfied no matter what value I choose? And you simply replace it with this rather ugly-looking logarithmic parameter. And the thing to note is that each of the factors on the top here is positively monotonic in the original parameter, and each of the 4 factors on the bottom is monotonically decreasing in the parameter, so the whole thing is monotonically increasing. It's a nice smooth function, and each one of these factors corresponds to one of these 8 bounds. So each of the 4 things on the top corresponds to one of the bounds on the left, and on the bottom to the ones on the right. And as q1, 2, 3 approaches any of these bounds, this parameter heads off to minus infinity or infinity. That's in some sense what stops you hitting them. And although it looks quite ugly, this is actually just a 3-way interaction parameter between x1, x2, and x3. So if you're used to working with discrete data, you'll probably have seen this kind of thing before. Okay, but that's giving me a variation-independent version of one of my parameters. Obviously, the other 6 are still variation-independent. And although these are the only bounds you need to satisfy, if you don't choose the first 6 parameters carefully, then you won't be able to satisfy this bound just with q1, 2, 3, because, for example, q1, 2 has to be greater than 0 in order for this range to have any, in order for it to be non-empty. So everything over here has to be bigger than everything over here, and that induces a whole bunch of new bounds. And some of them are quite strange looking, like this one up here, which actually corresponds to the sum of these 2 probabilities, which you wouldn't normally think of adding together, being positive. And if you sort of use these new inequalities in the same way that we did over here, you can get a variation-independent parameterization of this model. And all the parameters are quite nice. So I haven't written out the definition, but so here by psi1, 2 and psi1, 3, I mean log odds ratios, which are very familiar to people who work with discrete data. And psi1 and psi2 and psi3 are just logits of those events. The only strange parameter is this one here, which is the log odds ratio between x2 and x3 together with this other unusual looking bloke here, which is designed to ensure that these sorts of bounds are still satisfied. Okay, and that was all very easy because all the bounds were linear, so when I eliminated q1, 2, 3 by what's called Fourier-Motzkin elimination, I still had something which was linear, and I could carry on. Unfortunately, it's not completely useless because you can get away with some nonlinearity, so some models which don't have too many strange restrictions, you can use this method to come up with variation-independent parameterization. So this model, for example, had been conjectured that there was no variation-independent parameterization, but you can construct one with this method. Sometimes the model is a little bit too extreme, and you'll find that this method doesn't work. However, there is a sort of happy ending to it all, which is that you can I have a proof. It's not very constructive, but you can come up with a variation-independent parameterization of any model of this type, although you may not actually want to use it. Yeah, thanks.
Yes, I can ask a question.
Sure.
The first graph where you had the bidirected arcs and you had the 4 nodes, you're saying that they had to be complete. How is 2, 3, 4 complete?
So connected.
Oh, connected.
The word I used. Yeah, sorry. So I just mean that you can move from any node in the set to any other node without leaving the set.
Oh, okay.
Okay.
Okay, I guess we can thank Robin again.